Question 16 then begins with this compound, and it wants us to name it. So you can see first of all the longest continuous chain goes 1, 2, 3, 4, so it's bute, and it's saturated, no carbon-carbon double bonds, so it's an, don't forget the an. And then it's going to end in ol because of the OH group. So we have to decide which end to start numbering from in order to put the number in there. And the convention goes that whichever group is your ending, so the ol, which comes from the OH group, that takes priority to get the lowest number. So that means you have to number it this way round, so that the ol gets to be 2 rather than 3. So it's going to be butan 2 ol. And then of course carbon 3 has the methyl group attached, so it's 3 methyl butan 2 ol is the name of that compound. Then it wants a structural formula. So that just means that we've got to list the whole thing out all on one line, no hyphens. Okay, so if you put hyphens in, it's not going to be right for a structural formula. So it doesn't matter which end you start from, so let's start from this end. There is more than one way of doing this, but this is how I'm going to do it. So I'm just going to start with the CH3 there, and then say, right, here's the next carbon. It's going to be CH because you can see there's only one hydrogen there to take the bonds up to 4, so it's CH and then brackets CH3, okay, because this CH3 is a branch. This one again is going to be CH because you can see it's got 3 bonds drawn, so there's just one hydrogen left over, so CH. And then the OH doesn't really need to go in brackets, but you may as well put it in brackets because it, I think, just makes it a little bit clearer what's going on. And then we've got the CH3 at the end. So there are a number of ways to write the structural formula, but that would be fine for one of them. And then it says that we're going to, what does it say we're going to do? Yeah, we're going to do an acid catalyzed dehydration. So that reaction you need to know involves eliminating the OH group and then a hydrogen from one or other of the next door carbons, because that combination of an OH and a hydrogen will eliminate water, hence the dehydration. So we have a choice. We can eliminate a hydrogen from carbon 1 or from carbon 3. So if we look at what the possibilities are, if we eliminate from carbon 3, we're going to get a double bond here between those two, so we're going to get this, and the OH is gone, so that's one of your products. No EZ issues because you've got 2 methyl groups there, so if you flip them over it would still be the same. So that's one product. The other one will give us the double bond there, so we're going to get this with, again, the methyl group there. So those are the 2 alkenes, so that was a fairly straightforward one. Part 4 wants us to write an equation for what happens here when you take your compound and you treat it with sodium chloride and conch sulfuric acid. Now, this is a much easier question if you've learnt your reactions in advance. If you hadn't learnt it, what you might be inclined to do would be something like this, and then think, oh yeah, we're going to substitute chlorine for OH, which is true, and you might write that, and then look at what you need to do to balance it and write this down. And you think, oh yeah, that balances, great, job done. Unfortunately, that's garbage, and that's not what happens. And that's the problem with organic chemistry, that just because you can write an equation for it does not make it right. So that's not what the reaction is. That is the product. Okay, so this reaction is the one you learn as a way to make a haloalkane from an alcohol. That's the condition you need to memorize. But what happens is that in the pot, those 2 things react together to produce HCl, and what you put into the equation, easiest way to do it is just to put HCl, which is what you produce as a result of mixing those 2 things together, and then you can see that what's left over is the OH and a hydrogen from there, so you just get water as the other product. Okay, so that question is a real lesson in the fact that you have to memorize the reactions properly and not rely on making stuff up, because if you make it up, you probably got the equation wrong. Part B is asking us to complete the equation for this, for treatment of this compound with excess acidified potassium dichromate solution. Key word in that question is excess. Hopefully you noticed that and thought that when it says that, it usually means that it's going to react more than once with this compound. So what you're going to be looking at here is that you've got 3 functional groups, 3 OH groups, and you've got to ask one at a time, does that react with it, does that react with it, does that react with it? So that's the first thing. The second thing is to notice that it said refluxed, and that's important when it comes to the primary alcohol. Okay, so let's just go through. So from the left, this is a tertiary alcohol, okay, because that carbon has 3 other carbons attached to it. That means it cannot be oxidized by dichromate. So that one just stays as it is, so we can write that end down unaltered. This is a secondary alcohol because that carbon has 2 other carbons attached, and that means it can be oxidized just as far as a ketone. So that carbon is going to become C double bond O, like that. Now this one is a primary alcohol because the carbon just has 1 other carbon attached, and those, remember, can either be oxidized to an aldehyde or further oxidized to a carboxylic acid. But because it says refluxed, that means you keep oxidizing for a long time. You know you've got excess, there's plenty of oxidizing agent there. That means you're going to end up with the fully oxidized carboxylic acid. So the CH2 at the CH2OH at the end becomes COOH, and that's your product. Then you've got to turn that into a balanced equation. The easy way to do that is to remember these things in advance, and remember that when you oxidize to a carboxylic acid, it requires 2 magic oxygens and produces 1 water. So we can put 1 water there so far, and remember that we've got 2. When you oxidize a secondary alcohol to a ketone, that produces another water, so we can put 2H2O there, and that means that overall we're going to require 3 magic oxygens. If you weren't sure about the numbers of waters, then of course you can just check the balancing, because you know what you've got on the left hand side, so you can just count how many waters there need to be there. But just because it's an organic equation doesn't mean it doesn't need to balance, so those waters have got to be there. Part C, we have this compound, compound C, and 3 reactions we're asked to figure out what the products are. So starting at the top, you can see this is a carboxylic acid, and when you see that combination of a carboxylic acid with an alcohol and an acid catalyst, you think this is about esterification, which it is. So each of those COOH groups is going to be esterified, so let's just remind you how that works. Again, that word excess in the question was a big clue that told you that both of these are going to react. So if you want to figure out what an ester will be, you just draw your alcohol and your carboxylic acid back to back like that, and you remember that what happens in esterification is that you condense out the water by losing the OH group from the carboxylic acid and the hydrogen from the alcohol. So that condenses out, and the same here. And then you join together the fragments that are left. So that's lost, and that's lost, and you just join together what's left. So you can either just write it as a shorthand as COOCH3, and that would be fine. Be a bit careful at this end because you've got to make it go like that to show that the carbon's connected up. Or you can just draw it out any way you like. You can draw out a displayed formula like that, or you can use a skeletal formula. Any of these are fine, but that's what your ester is. Okay, so just the methyl ester at both ends. So the clues to that, we're seeing that combination, carboxylic acid, alcohol. That should ring a huge loud bell that says ester, and the word excess should remind you that both ends can react. Now this middle one, steam and phosphoric acid, again, if you've learnt your reactions, you know straight away that's how you add water to an alkene. So you add an OH to one end of the double bond, hydrogen to the other. So that makes that one very easy, because all we have to do is just copy it out, but without the double bond in the middle, just a single bond now. And instead of the pi bond, we have an H at one end, which of course in a skeletal formula you don't see, but it's now there, and you have an OH at the other end. So that's your product. And finally we want polymerization. So you've got to think, well, what sort of polymerization is it going to be? Addition or condensation? So you've got the carboxylic acid group, which might make you think condensation, but there's nothing for it to condense with. Remember, these can undergo condensation, polymerization, if you also have alcohol groups to make a polyester, or if you have amine groups to make a polyamide, but you have neither of those things. So the only way it can polymerize is using that alkene group in the middle to make an addition polymer. Now you could work out what that would look like quite easily, just keeping the skeletal formula, because remember, all that happens when you make an addition polymer is that the pi bond breaks, just as in all the other addition reactions, and the electrons are then used to make the linker bonds to the next repeat unit. So at the two ends of where the double bond was, you're now going to get a linker bond there and a linker bond here. If you just draw a bracket around that with the linker bond going through it, that makes it clear that it is a linker bond, and that's kind of quite important. So that looks a bit weird, but that's a perfectly respectable way to do it. On the other hand, if you've learnt to do polymerization by sort of always thinking of your monomer like this, then of course it's easy enough to redraw that in that format and say, right, here's my monomer, and all you do to turn that into a repeat unit is again to say, right, it won't have a pi bond anymore, so we'll just have a single bond across there, and here are my two linker bonds sticking out at the ends. Again, drawing a bracket around it, putting the linker bonds through is a good plan, because it makes it clear that that's what these are, just linker bonds. So those are just two ways of drawing the same thing, but make sure you spotted that that was addition polymerization. Don't be fooled by these, because they need something to condense with if they're going to be involved in making the polymer.